Since Bangalore. So already I have given my talk on I believe Tuesday evening. So my talk was about how we can interact, you know, and make the software interact with the hardware, and not only interaction. Okay, visualization of data is also a critical aspect. So that also we mostly focused on how the software tools can interact with hardware, extract the data, and convert into format which visualization can be done in a very good manner. And also this data should not be local. We need to access data from anywhere. So in order to do that, okay, we explored certain cloud options. Okay, there are thousands of cloud options available, but ultimately we have to go for something which is open source, something which is easy to use, and which has open protocol support. So with that aspect, we selected Google's Firebase, which has an option of real-time database which can be accessed over anywhere over the world. Um, Primarily, it can be accessed by using unsecured means, but with further configuration and other settings, we can make it more secure in such a way that only after logging in, okay, we can access the particular data. So we can make it more secure as well. But other clouds are also available, like if you say IBM Bluemix, AWS, okay, which have more support for infrastructure, security wise, cyber security and other things. But ultimately these are costly tools. Okay, if you have already have the subscription, Labview offers APIs. When I say APIs, these are some functions which when you install and work with Labview, okay, like other tools like Python also, if you see there is packages available, okay, which if you go to command line and type pip, okay, it's going to have these libraries which can be installed and start your work right away. But here in Labview, we have to install libraries like pip library. If you have to install certain libraries from IBM or AWS or whatever it is, okay, if you install it, it's going to be accessible, right? So but easy to use is going to be free to use as well. Okay, but some there are more easy to use, but there are paid access as well, right? So that is about the previous sessions, that is acquiring data and putting into cloud so that it can be accessed over any method. Now what we're going to see is ultimately we are going to see about a tool. I mean, we are going to see about control system design and simulation. That is using the same graphical system design platform, how we can perform control system operations. Okay, before performing the actual operations, what are things to consider, how we can simulate them in the graphical environment, the total system and plant, and what are the tools which we have to offer. So in order to show that, let me just share my screen and let us see the insights about the same. So ultimately I have shared the screen right now. Okay, hopefully it's visible.
Yes, sir.
Yes, thank you for confirming. So the reason why people will go for control system design and simulation, okay, for IoT systems is, as everyone knows, that in order to control remote devices, some of the control systems are deployed in remote places. Like you can say it's going to be deployed in forest, okay, running some random um, experiments, collecting data, okay, critical data. Okay, not only random forest based data, okay, and what I'm talking about, okay, this could be weather data which should be collected over a large period. I mean large period as well as over a very large area as well. So distributed systems also should come into picture. So it should not be like a very generic embedded system which can do everything. Okay, there should be a environment which is very fit. Okay, it's a very suitable fit for designing control systems as well, specifically modified for such operations. So we are going to see about these things, how to simulate the control system, what are steps involved in that, and implementation discussion also perhaps we can do. Okay, so that the if you take a control system, okay, typically it will have closed loop systems will be there, and for the closed loop systems maybe we need to set points. Okay, let's say if there is a control system, temperature control system is there, furnace. Okay, maybe you want to control the furnace from anywhere of the globe, maybe at least for testing purpose. Okay, so that architecture should support IIoT architecture. Right? So that is going to be the case. Or sometimes, let's say if you're into aerospace and you want to, uh, check the set point for turbines, okay, aircraft turbines, okay, temperature and pressure set points you want to set. Okay, so in that case also you need to have some, remote connectivity options, and this should happen in real time to control the controlling and sending data and all. So let us see what are the options available. Already we have seen about IoT systems. Okay, we are going to see about what are the options with respect to designing a modeling of control systems in Labview. So as we all know, when we all know what control system is, it's going to be the interconnection of either an electrical or mechanical or the software systems in order to perform certain tasks, right? So this could be a task which is related to when we give some input, okay, it should perform some operation. Maybe this operation is just going to be linear, like when I give some input, it's going to perform some operation. Or it could be a system which is going to get some input, but apart from getting input, it's going to get the feedback as well as the output. What is currently happening in the output, that data also is going to get, and it's going to perform the closed loop operation. So several types of control system and different types of um, industries and products will be used. Okay, you can say for furnace operation, or maybe for power plant operation inside a boiler. Okay, maybe you need to use certain um, a control system inside to either operate the furnace or motor, okay, whatever it is. Or for precision tools, okay, in order to adjust the x and y know, coordinates. Okay, let's say you're going to do 3D printing. Okay, that also requires a control system there. And there is no introduction for control system for aircrafts. Okay, so if you look at most of the airplanes right now, it's going to be autopilot is going to be there. Okay, which is going to take into the consideration of uh, inertial navigation systems. Okay, or GPS navigation systems is going to take it into consideration. It's going to plot the course and it's going to fly on its own. Okay, adjusting the angle, okay, the yaw, okay, all those kind of pitch. Okay, these values is going to adjust and it's going to reach the destination, and so on and so forth. You can go keep on going. A control system is going to be the part and parcel of our life, right? So implementing this, we have several tools available in the market, but how engineers and scientists can easily, okay, do a simple simulation, and starting with a simple simulation, how they can step by step implement incremental implementation, doing at the final. Okay, we need to get the product, okay, product level simulation. Okay, so that is going to be the critical factor, right? So there are several tools available, like several systems are also available, okay, which needs to be simulated. Okay, I'm sure subsystems and all everyone would be knowing. Okay, so let me just skip it. Okay, what control system is? So what type of control systems everyone knows. So ultimately, what I'm trying to say is how Labview can help us implement the control system. Okay, so these things and all everyone will be knowing about. So in LabVIEW, implementation of the same requires certain process. Okay, so it's a 5-step process. Okay, where it involves modeling. Okay, modeling in the sense mathematical modeling of the system. Okay, creating a plant. So the plant, there are different types of models available. Okay, inside LabVIEW itself. So mathematical modeling, you can do it without software tool also. Okay, but for simulation purpose, if you want to perform the simulation with respect to time, variation, the time variant or simulation, if you want to do, okay, we need to have a model. So that model, after implementing, let's say we know what is the equation of that model. In order to implement it, okay, software model should be established. So basically, we are going to bring the model inside software. Okay, software and loop, you can say. So next is going to be the controller design. Okay, after creating the model, it only makes sense for us to create a controller for it in the software itself and evaluate that model, right? So before we actually create the embedded system, which is intended to control the real circuit, we need to check, okay, whether we need to check everything into consideration, whether we have considered every parameter into the model, into the controller design. Okay, whether initial controller, whatever you design, whether it's a good fit for the actual hardware, considering all these parameters. Okay, whether it's working properly, it's satisfactory or not. Okay, all those things first needs to be tested with a very good accuracy. Okay, and at least satisfactory accuracy should be tested. After design the controller, okay, after checking all the parameters, next is going to be the simulation. Okay, combining the model and the controller together. Okay, we need to perform certain simulation, right? So it could be a PID controller with our model, right? So once that is done, we need to fine tune it. Okay, PID will not, at the stretch itself, it will not be fit properly. Okay, perhaps we need to check whether it is performing accurately, or whether it needs to have some sort of tuning is required. Okay, when we say PID, okay, either it could be a P controller, a PI controller, a PD controller, or full PID controller should be required. Again, that depends on certain models. I mean, it depends on the models and depends on how fast you want the convergence to happen, right? So that after verifying, the most important thing is how we can do the implementation without jumping platforms. So now it's going to be a little bit tricky process, because most of the people who do control system modeling, they do it in a software which only supports software simulation. And most of the people will be clueless when they want to make that software into reality. So maybe that software does not support hardware integration. Even if it does not support a wide variety, or it does not support to the rate at which they want the control to happen. So let us see how Labview is going to be different from that point. So before we get any further, let me know if anyone has any questions, so that I'll try to clarify them.
Any questions, please? Sir, some settings has been changed. I think your screen sharing.
Yes, ma'am. How does it appear? Is there any problem?
Yes, yes, it is not coming in full screen like that. Some settings has been changed. I think I don't know by whom.
Okay, let me just check one second.
Yes.
I'll stop sharing once.
Mm.
Now, ma'am?
Now it is okay, sir.
Everything's fine, right?
Yes, yes, now it is coming.
Maybe due to some issue. Fine, ma'am. Okay, if no one has any questions, then perhaps I would just like to go to the next step, okay, in this modeling and other things. So yes, so if you see, Labview essentially supports two types of modeling. Okay, one, it supports classical method that is most favorite method for most of the system engineers. Okay, that is transfer function model. Okay, so even in academy also, I believe the transfer function model will be mostly focused. Okay, but in research and other advanced studies, okay, people will prefer going for state space model as well. So that is also available here. Okay, so I'm sure that most of you would be aware, already aware of, more than me better. So you'll be aware of both of these methods. There are other methods also. Okay, so Labview essentially supports these two methods. Okay, there's one more method as well. We'll see that in tool itself. Right. So in order to understand how the modeling is done, okay, we are going to see an example of modeling of a DC motor. Okay, for to understand the control system creation. So DC motor is going to be the a mechanical device which is going to convert the electrical energy to mechanical energy. Okay, we are going to control the aspect of speed of the DC motor. Okay, in order to do that, ideally we need to have an actual DC motor and actual motor drivers. Okay, once we in order to control that motor, either we need to go for a microprocessor and microcontroller to control that motor driver, which in turn converts the the commands whatever we give to it, okay, in terms of electrical output, and that electrical output will be given to the motor, and that motor will depending on the command we give, it's going to rotate at that particular speed. And depending on its open loop or closed loop, we'll get the feedback as well. Okay, either you'll get the speed measurement or position measurement. And once we do that, we'll be able to do the closed loop as well. But before we actually get this motor and the drivers and all those things, okay, it makes sense for us to do a simulation at least. Okay, so that we already everyone would have been knowing. Okay, in order to model that motor, okay, transfer function, or whatever we are familiar with, okay, we can go for that mathematical model. Labview essentially supports transfer function modeling, state space modeling. So here we have, for our understanding, a DC motor which we are going to model. So to do this modeling, we are going to prefer using um, Labview. So here we have this Labview front panel block diagram, both of which is available. So I'm sure everyone would have already known about front panel block diagram the first day. The second day also we extensively focus on that. And here you could find that the generic Labview functions are already here. Okay, but what we're going to go very specifically into is, okay, we're going to go for something called control and simulation. Okay, this makes it essentially possible for the control and simulation to happen. Right. So for this toolkit, already link has been already, I believe it has been shared. Okay, so if you want to try it out, okay, you have it available. But normally, if you don't install that with basic Labview, you might be seeing these two options. Okay, that is PID control is already available inside Labview, and fuzzy logic is also already available. Right. So we'll not be covering much about anything about fuzzy logic because it's out of the scope for us now. Okay, but we'll be seeing about control and simulation. Okay, this is the very important topic for us. So control and simulation, and here, in order to build the model, okay, we'll be focusing on this simulation paradigm because this is what makes the simulation possible. And in order to build the model, okay, we will be having something called okay, not here. First, now to build the model, okay, we'll not go for simulation. Okay, we'll be going for control design. Okay, first, you need to build the model. And here, if you see, there are different types of control design platforms available. Okay, out of which the simplest thing which you need to go for is model construction. In order to create the model, you go for model construction. So here, there you go. Okay, you have a state-based modeling available. Okay, transfer function model is available. And the third model, which is also used by researchers and scientists, is zero pole gain model. Okay, I'm not sure how um, popular this is in the academia or research section. Okay, but I have seen one or two cases where people prefer this as well. Okay, if you're familiar with it, this model is also available. Okay, this modeling we'll do first. So in Labview, modeling is also possible, and visualization of the um, equation is also available as a tool, right? And there are plenty of other things are also available as a tool, okay, which you can perhaps, you know, experience using your toolkits. So first, let us focus on model construction. What does it that makes the model construction easy in Labview or makes it hard in Labview? So I'm going to use a transfer function model here. So let me just pick and place it, the transfer function model. So to construct transfer function model, this is the function which we use. And here, for transfer function, we have different types of transfer function. Okay, either it's going to be single input and single output, where you get single parameter inside, and depending on the response, okay, you're going to get single output. Sometimes, okay, we'll be going for multiple input, multiple output. It will be multi-structure, control system also will be there. So that is also equally possible, right? And in that itself, sometimes we already would be knowing about the transfer function values by default. Okay, a fixed model may also be there. Sometimes perhaps we'll be having a parameters varying. Okay, maybe today you'll be working with one type of motor with the fixed components. Okay, or tomorrow maybe you'll be working with a different model of the motor. But the transfer function equation for that motor may be same. Okay, but only the parameters like the parameters like the motor constant or resistance. Okay, motor, the motor armature resistance or moment of inertia. Okay, those parameters might change, only change. Okay, so for different motors, if that's going to happen, then you need to make a model a little bit, um, you know, reusable. Okay, we call it as reusable. So let's focus on that. So let's say in this case, this is the transfer function model, okay, where it says um, omega m by Vm, okay, output by input is transfer function, and omega m is output, which is basically the position, okay, divided by Vm, which is going to be the voltage. For the applied voltage, you get the change in the position, and sorry, this is speed. Okay, position means to be theta. So let's not worry about it that much. So here we have the Km divided by Jm RMS plus Km square. So we are going to say how we can fill, okay, the values. Okay, there's a numerator component and denominator component. So in Labview, we have both numerator and denominator as inputs, which I can right click on the terminal and create a control. And again create another one more value. And here again we have a denominator. So how this fills in and maps it as a transfer function is essentially for numerator or denominator. Okay, this is basically the zeroth coefficient. Okay, so zeroth coefficient in the sense whatever value comes here, okay, it's going to be the power of s power 0. S power 0 is nothing but 1. Okay, the constant value. And next one is going to be the coefficient of s power 1. So whatever value we give here will be multiplied with s. Okay, s naught plus s1 plus s2. And this is going to be s power 2. Similarly, below also the same thing happens. So what happens next? So now we need to calculate, okay, Km. So Km means 0.0280, it says. Okay, so here also we have to do 0.0280. Okay, it doesn't have S naught or S1. I mean, no other coefficients are there. Next is going to be Km square. The Km square is going to be S naught's coefficient. Next one, Jm into Rm is S's coefficient. Okay, S power 1's coefficient. So we need to calculate the Km square. So what I'll do is here I need to pull the Km square in the denominator, which is S power 0's coefficient. So again I need to calculate it. So the value states as 0.028 square. So when I click on it, such as the value it is appearing. So I'll just copy it and paste it here. Km square into Jm into Rm. Okay, Jm into Rm. So 9.64 into, so here again standard calculator will not be sufficient. So let me just use a scientific calculator, and 9.64 into 10 power 6. Okay, so this will be tricky in calculator. So rather what I'll do is I'll do the calculation in Labview using multiply function, and I'll create all controls indicators. I'll say n.64 e power minus 6. Okay, so this into Rm, this is nothing but 3.3. So it's written as 3.1812 e power 5. This is going to be the power of yes. This is the actual value. So this we had to calculate essentially. And of course, the same thing will happen in other tools also, but that's not the point what I'm trying to say. So once we do all these things, filling the numerical coefficient and denominator coefficient, the output of which is going to be a transfer function. Okay, a model is created in the program. Numerator and denominator. So you may ask, what's the difference between this and this? It looks like same. But this is a unstructured model, whatever we have created. We have given as input to this function. This created a model with value, information like what's the type of meaning of the model, and what is the sampling, the time at which this model is running. Yeah, and numerical denominator also is given. So it's you can say it's like a structured model, right? So if you give that value here, it will be created as a model and it will be an organized data structure, right? So once this is created, this is not a very good way to visualize your equation of transfer function. Yes. So what we would do is we would go for in the control simulation toolkit itself, because most of people will be loving to view the equation in the form of an equation instead of as a numbers. Labview offers visualization tools. Okay, in the control system design, control design, model construction. Apart from thousands of other functions, you have something called CD draw, okay, where you can draw any type of model you want.
Excuse me, sir.
Yes.
So these options are not available in my Labview which I had installed.
Um, Sir, actually, we have already shared the toolkit for this design simulation toolkit link we have shared. I hope that was shared to you.
Yes, sir.
So yeah, once you install that, only this will not come natively. Okay, so some features will not come natively. Like there are plenty of other add-ons are available. Okay, so like Elvis MX
So how
second
to add them?
once you get the link for installation, okay, you have to download it and install it as a separate add-on.
Okay. So
Okay,
because
so
in
even if you go
when I
to
right clicking on this here in the control and simulation, I'm only getting the PID and fuzzy logic.
yes, exactly. So we have to download and install something called Control Design Simulation Module. Okay, once you download and install that,
Okay.
if you install it, it is going to come. You have to select the um the you know version.
So I had installed 2019 version.
So perhaps you can try and just try checking whether it is available for 2019. So check it out and let me know. Yeah,
Okay. Thank you so much, sir.
yeah. So once you know create this, okay, this function is going to be useful for visualization purpose. Okay, now visualization in the sense, okay, you have to give in for this function an input of the transfer function model which we just created. Okay, so this is what will be accepted by all other functions. It's a standard format. Okay, if we try to create something out of our own and try to implement it, okay, that's the highest chance that it will never work. Okay, so that's the reason why this has been used just to create the model. So I'll give it as input to this function, and output what we get is, okay, the output what we get is equation, where you can right click on it and create an indicator. So if you run this program, what you essentially see is an equation format of the transfer function inputs whatever we are given. Okay, we have numerical denominator like this format, and this has come as an equation. So for people who are very interested in the equation modeling, okay, this would be a good to use tool. But this is a static, model formation. Okay, so this will not be applicable in places, at least in industries where you want to, today you'll be working with one model, tomorrow you'll be, requested for a report of another model. Okay, so just by varying the parameters, you should be quickly able to, create the equations and plot it. So in that case, you need to have a way to, implement uh, parameter wise. Okay, so how that goes about is quite simple again. Instead of using this function, we will just select the drop down list, and we have something called symbolic. Okay, in the first function, instead of going for normal SISO or normal MIMO, we'll be going for symbolic model. This which supports in terms of symbolic values. Okay, when I say symbolic values, the inputs will be in terms of symbols. Okay, transfer function modeling will be done in terms of symbols. Like instead of giving 0.0280, I will give km, and separately I'll define the value of km somewhere else, and I'll say rm jm into rm and km square. This model I will create, and somewhere else I will say this is the value for km, this is the value for rm, this is the value for jm. So this is the standardized format for a DC motor. But today or tomorrow or day after tomorrow, you will be keep on changing only the values, and perhaps maybe it's an industrial environment where you're working with different model motors, or maybe you're trying to do research, but you want to find out which motor is the best fit for your needs. So you're just experimenting with different values. So for that sake, it's best to use symbolic values. So again and again, you don't need to calculate it. So how this works is the same format will be used. Okay, symbolic numerical replica. Again, it will create a array wise controls will create for both numerical and denominator. But there is a subtle difference. Here also I have numerical control denominator. The only difference is here is this is a string array. Okay, meaning instead of giving us a number, okay, you will say what is the constant name. Okay, so here is, let's say km is there, right? Instead of saying 0.00280, I'll say k. Can you? I mean, this is numerator. I'll say this is k. Okay, and here denominator we have to consider first k square should be there. K square is k power 2. Okay, km square is k power 2. That is the constants coefficient. Next, yes, coefficient should be given at 1. Okay, always lab is counting will start from 0, 0, 1. So this is j into r. J into, we have to put, we have to use star r. So we'll define it as a fixed value. And the value, however, for these things, we have to give as a variable here at below. Okay, so the variable values we have to give separately. So this is an
It
array
is
of,
only for 2021. It is not for 2019.
yeah. So for 2019, maybe right now I will just go ahead with this. But for
Okay.
2018 we have shared the link. 2019 perhaps I have to look
So
at
you have
the
shared
proper.
the 2018 link, but it was not working. That's why I had downloaded 2019.
Is it?
Yes, sir.
Okay, let me just find it my team. Let me just do a quick check. Okay, if it is
Okay.
available, perhaps I'll share it with you.
Okay. Thank you so much, sir. So
Yeah.
because my system is 32-bit only.
Okay, I understand.
Thank you,
So
sir.
yeah. So here we have variables. Okay. So variables in the sense here will be specifying, the values as names, j or k or r, and the subsequent values we will give it over here so that it will automatically map and it will, do the calculations and all. We don't have to worry about those calculations. Okay. And values also, we have to give it properly. The only thing about values is, it has only values up to 2 decimal points. So that can be, corrected by right clicking on these values inside. We have something called data entry. You can do for one, it will be applicable for all. You can go for display format and you can say you need up to, let's say, 10 digits of, precision. Okay, it will by default it will only give 2, but our equation it will may go up to 7 or so. So it's best if you go for up to 10. Okay, I'll just give okay. And now time to map the values. Okay, k, which is nothing but 0.0280. 0.0280. And trailing zeros also will come. If you don't want it again in the, you can you can right click on the data entry. You can go display format. Here there is an option called as hide trailing zeros. Up to 10 digits it may come. If you don't want any zeros behind, you can just do the hide trailing zeros. So next is J. 9.64 e power minus 6. So it has been manipulated in this particular format. So it's J. R is 3.3. Okay. So once you do that and just run this code again, there's nothing which is going to change, okay, because whatever you have done before, the same thing only has we are done now. The only thing is we could perhaps try changing these values, and here also we can change the changes. So if I change to 0.03, here we can see some change in the values. Okay, so 0.7, change it and run this. Okay, it's going to be variable now. Right, so now this could be used only for purpose of DC motor. Okay, I don't even need to have it as a constant in control. I can right click on this and change to constant, so that no one can able to change it when the program is running. So we have here this. Okay, so this is the modeling part. Okay, let me just restore it to 0.028, and there you go. Okay, we get these values properly. Fine. So now we have done with the modeling. Okay, up to this only is important. Okay, this is pretty much optional because some people will be very much interested in equation modeling. So if that is the case, then you can use this. Okay, but if you're not very fond of equation modeling, then you can discard it. Okay, there is no pressure in doing so. Okay, so this is model. Okay, now that we have modeled it, next is going to be the controller design. Okay, again, controller design, we have plenty of types of controller. We have PID, we have fuzzy logic. Nowadays there are adaptive control systems. Okay, a lot of things have come into the picture. Okay, but you can step by step go one by one as well. But now we are going to see how to implement a PID controller and what are the things which we need to consider before we actually start implementing the PID controller. Okay, first we need to design it. Okay, let's whatever parameters we decide. Okay, we need to check whether it's a proper value or it's not a proper value. Okay, so first we need to evaluate in the control system. Okay. So this needs to happen. So, but modeling, if anyone has any questions, please don't hesitate to ask questions. You can drop your question in the chat and let me clarify. Okay, perhaps the best thing to do is if you have any questions, you can let me know. Okay, so far only one question has come. That is due to Labview, software issue. So that the link 2019, we have shared link for 2018, both of them. But if you want for 2019, maybe I'll put a word to my team and they will get back to you.
Okay, sir.
Yeah. So here, what options to consider for PID controller? How to model the PID controller? So for that, first we need to understand how the model is inside internally. Okay, so when you go for to implement a closed loop control, okay, so this is how we need to consider the model. Okay, first we may have a motor. Okay, motor is coupled to PID controller in this format. Okay, and it is going to be in series. Next is going to be the Maybe we may need to control the speed of the motor, or maybe we need to control the position of the motor. In this case, we are going to control the position. Okay, so we're going to control the position. So the output of this particular plant model is going to be the angular velocity, which we will, um, differentiate, or sorry, integrate, okay, to get the, I mean the position. So once we integrate, okay, we are going to pass it to the set point value. I mean, as an error of the signal, we are going to pass it as feedback. Okay, this is going to be the proper set point, and that, um, you know difference, we are going to feed it as the error to the PAD. Okay, so in theory, this everyone would have in control system, they might have seen. Okay, but how to implement this in Labview? Okay, so there are other tools also available. Okay, there is no denial about that. So how does how Labview is supporting for the same? So in same control simulation design, the same, okay, not simulation, okay, control design, same, model construction. Okay, you have a lot of state space model, transfer function model, zero pole gain model. Okay, using transfer function model also, if you know how to construct transfer function of a model of a PID, okay, it's going to be essentially an equation. Instead, there is already a PID model construction is available. Okay, apart from PID model, there is also lead lag compensator controller is available. Okay, filter model creation is available. First order model, second order models. So templates are available here essentially. Okay, so it's quick to drag and drop, easy to use. Okay, so maybe easy to use part may not be applicable for everyone. Okay, but there is a steep, I mean, there's a easy, I mean, there's a very slope, I mean, learning curve at least for most of the people. The construct PID model is what we're going to use. So here we are going to have a PID model constructor is going to be available, okay, which depends on what value we have selected. Okay, so there is going to be an academic model, a PID academic, mean during the academic learning, the people are normally used to do proportional gain for integral instead of giving integral gain. Some universities, okay, they prefer using integral time and derivative time as inputs, okay, instead of giving it as KP, KD. Okay, so in the research also, most of this is preferred. Okay, but there is also other versions of the same. Okay, we have PID parallel, okay, where PID all of them will run in parallel, okay, collect data and process it. Okay, there is also a series of PID. Okay, P will be first, I will be second, T will be third. Okay, I'll be for this, I'll be using PID continuous and give values like PKP, KI, KD. Proportional gain, integral gain, derivative gain. So again, just like this part where it's going to keep changing, values are going to change. Here also KP, KD value will not be fixed. At least not in the beginning, it will never be fixed because we need to maybe fine tune it. Okay, whether our system, our values, whatever again, the KP, KD are suitable for the system, whatever we have selected. Okay, it may not be always the case. So maybe it will keep on changing. So how we are going to, fine tune it? How this can be made easier? Okay, we will create as controls essentially. Okay, we'll say proportional, integral, and derivative gain here, where we can create them as controls and keep changing the values and see the responses. So we have the model plant. Okay, it's going to be the plant. Here we have the controller. And for this controller also, the output is going to be the transfer function. If you want to look at the transfer function of this also, maybe we copy paste this particular function, which is used to visualize the transfer function as an equation. So this is the equation of the motor model. You can name them conveniently. This is going to be the equation of controller. So this could be, maybe it could be 10. This could be, 0.005. This could be 0.001, let's say, for instance. So this will create the transfer function model for the same. Now that we have the plant as well as controller, okay, next we need to perform the operation of the closed loop system. We need to combine the PID with the motor. Now combining part is going to be slightly easier. Okay, I'm not going to say it's going to be harder, but it's going to be slightly easier, as in how to combine them is going to be the question. Okay, so model construction, we have this, model construction pass is available. Okay, however, for combining the models, okay, we have certain tools. Okay, model introduction is available. Okay, so this is what we're going to use in control simulation, control design. Model introduction is what we're going to use. So here you can say we can add models, subtract models, multiply models, divide models, whatever you want to perform to a model, it's available. So now what we're going to do is, right now we're just going to convert both of them in series. Okay, that's what is intended to be done. So first we'll connect the controller. Second we'll connect the model. Okay, so we'll connect both transfer function and transfer function. Some people will do the modeling in the transfer function. Some people will create this one in the transfer. I mean the PID controller and state space. So all three combinations. Okay, so state space to state space, state space to transfer function, state space to zero pole gain, or some intermix of components are available already. Right. So you don't need to check it automatically, which I can do select manually. Okay, the moment you connect a transfer function here and state space here, this will automatically detect and it will select the appropriate ways. Okay, if you connect something which is not accepted, then the program will not run at all. Okay, so we have done the model, we have done the controller, and we have this here. The controller, model. The next is going to be, after getting this input, okay, I mean, after giving input of voltage to this, okay, the output of the motor model is going to be the push, I mean, velocity. Okay, to control the motor, okay, I'm going to integrate the speed velocity into, a, perhaps a push, okay, the angle. So in order to do that, here it says 1 by S. So in order to implement that, again the same thing, control simulation, control design, model construction. I will go for transfer function modeling. I'll say what is appropriately used. Okay, so 1 by S means, so this is going to be 1, and S means it's going to have components of, there's going to be no constant. Okay, it's going to have only one coefficient of S. So 1 by S. So this also we're going to connect in series to this path. I'm going to copy and paste this. This as input model 1, and this as output. Now we need to give the feedback. Okay, so feedback, we don't need to give any feedback from here to here, or we're not going to give any inputs right now. So in order to achieve that, there is already a function again, okay, in the control system design, model intervention. There is a function called as feedback is already available. So if you see, there is no manipulation of the feedback here. Okay, so only thing which I need to give is only model 1 is what I need to give. Okay, so there is nothing I'm not going to give. So only this I'm going to give. The other one I'm just going to keep it as it is. Okay, maybe it's going to be considered as unity feedback. It's just feedback. That's it. So the output of this is going to be the whole system. Okay, which if you want to visualize as an equation, you can do by copy pasting this particular portion. Okay, you can say this is the system model. Motor model, controller model, system model. Now, ultimately, the point of doing this modeling is to evaluate whether this is a good fit or not, right? So whether the PID values are going to be properly working, it's achieving the proper simulation parameters, okay, so that we can proceed for implementation. We'll go for vision and motion. I mean, not sorry, control simulation. So right now we have seen control design, we have seen model construction. Okay, we have seen how to integrate all the models. Okay, so up to this, I hope everything is fine. Okay, the point of this is to evaluate how the model is, gelling into the system. Okay, next is to extract important information from that. Okay, so we can run some certain steps like time response we can do. Okay, we can try running system response. Okay, we can get the parametric time response. Okay, apart from getting the waveform, okay, we need to check how it works in terms of measurements, like whether what is it the time period of rise time, what is the time period of the what is the percentage of the peak overshoot, okay, how much peak overshoot we achieved. Okay, all those values as numeric value if we get, it's going to be very helpful, right? So see response, step response. If you want to get a step response of the closed loop system, okay, we can perhaps try going for this function. Okay, so there are plenty of other functions also. Like if you want to get a frequency response, you have that. Okay, you have other dynamic characteristics. Okay, so plenty of options are available here, right? So let's just try time response. Okay, so I'm just going to go for step response. And just give it as input. The output which I'm going to get is step response data, the graph. So let me just start with Unity and run this. So if I run this program, you can see that with proportional gain of 1, you can see there is a peak overshoot. Okay, up to 20% peak overshoot is there. Then again it comes back. Again it goes down here. The control system is working fine. Okay, so you can see that it settles down. Ultimately, it settles down to 1. Right? So it works. So this happens because we have done a step response here. Okay, so we have given 1 as input. So it takes time for us to set us from 0 to 1 for some time. Okay, let's say it's coming up to 400 milliseconds, I guess. Okay, you can try increasing the 10. Okay, to make it trying to reduce the um, price time. You can see that instead of approaching the 1 within certain time, instead of coming for, if you give 1, okay, you can see that it's going to take certain time. Okay, maybe it's going to take some value, okay, 50 or 40. If you wanted to come before that, maybe try increasing the proportional gain, so the rise time is going to reduce. At the same time, it's going to become a little bit unstable as well. The stability is going to get affected. So these things, I believe, there's already a you can say like a quick the guide, okay, to tune it quickly. Okay, so what happens when you do proportional gain increase, okay, derivative gain, or integral gain. So when you increase this, okay, it decreases the rise time. So the more I give, okay, it's going to um, approach the value as quick as possible. But sometimes it causes steady state error. It has steady state error there. Okay, and it reacts to proportional to the error. The more the error, the more reaction it will give as well. So in order to remedy that, then you have to go for derivative. You have to add derivative. Okay, so um, let's try adding some derivative values. Although there are certain formulas, okay, to derive that, you can also do trial and error as well. Okay, so let me just start with 0.01. Oh, sorry. So 0.01. You can try this one continuously and start increasing the values to check. So you can see that it's proportional gain has decreased the rise time, but in order to remedy, okay, the overshoot, okay, and the stability, increase the stability, I'm increasing the derivative gain. You can see that it has come up till this point. It has almost flat. Okay. So this itself looks good, okay, to be honest. But if you want to experiment by adding, integral gain, okay, it says it eliminates the steady state error. You consider adding some integral gain as well. In this case, I don't think it's required. Okay, because when you add it, it's going to increase the settling time. Okay, it's going to add more, steady time and settling time as well. So, which is not a desirable factor. So even though it looks like a straight line, okay, as a matter of fact, lot of data has come into picture, okay, which you can, try checking out by going to 0.5, 0.3. Okay, it has made the remedy much more simpler, maybe. So if you have it as 0, okay, this much effect has come up. But if you add certain integral gain, I don't think much changes occurred. Okay, maybe my eyes are not trained to understand what's happening here. So maybe it's time to go for using numerical values. So instead of relying the data, from my eyes, okay, what I can do is I have something called parametric time response. Okay, so in this case, I get parameter data. Okay, here also I'll get the parametric data itself. Okay, so if you see step response data will come. I don't have to go for another function. So you can see here rise time, peak time, overshoot, steady state error. Okay, all this information you can see. So steady state gain is 1. Okay, which means it's perfect. So rise time is less than 0.003. Okay, when we add integral gain. So this is with integral gain. Let me just remove this integral gain and run this program again. So this is with, that is without. So as you can see, with integral gain, slight decrease in rise time, which is good. But with integral gain, you can see that there is a slight overshoot as well. Okay, so peak time, it is also with it has increased. Okay, so and steady state error is going to 5. So for this system, okay, I believe that this does not require an integral gain as well. So we could discard it. So here also, if you see, it does the step response only, but in this case, we get the parametric values. Okay, there are other types of responses as well, which you can feel free to try, but maybe you may not get the expected data or whatever. So similarly, we have a lot of other tools as well. Okay. So this is how we model using, you know, NI, Labview, and control the system design toolkit. If anyone has any questions, please let me know. So I guess no questions. So let me continue then. Okay, now that we have fixed values for these proportional gain, derivative gain, theoretically this looks good. Okay, the mathematical modeling looks good. Okay, but we need to look this in something similar to real time. Okay, how embedded system or how the control system, the software is going to control the actual hardware is going to react. Okay, that level of modeling also needs to be done. Okay, something called a HIL. This is modeling. Okay, we need to perform some software and loop. Okay, and check how this is going to work in real, inside a loop which is running inside the hardware. So how do we go about that in that case? Again, we're going to use some sort of software to achieve it. I mean, we are not going to create anything from scratch. I mean, we are going to do programming from scratch again, but the model is already created by using this function. So there's absolutely no reason, okay, for us to do this again and again. So once we are familiar with this, let's say we have evaluated the model. This rise time is significantly, let's say it's, um, you can say it's no satisfactory. So now we need to check whether this will work in real time the same way. So instead of having this as a variable, let's say I've already fixed the values. I'll change this to constant such that it's not going to occupy the very limited space in the front panel. So we have the model here. Now we need to evaluate how it's going to work in real time. Okay, as we already saw, Labview is capable of interacting with hardwares. Okay, maybe we need to build a control system and controller and control system. Okay, and get data from some sort of sensor, run some operation, the control system operation on algorithm. Okay, and try to actuate some sensor to bring the data in control, check. So before we build that, we need to first evaluate it, right? So in order to do that, also inside Labview's control simulation toolkit, okay, we have a simulation toolbox available. Okay, simulation toolbox. Okay, and inside this, there is a very important tool, okay, called as control and simulation loop. Okay, one might ask, what is the purpose of this loop? Because inside here we have this while loop and for loop. Why not use this, and why use specifically this? Okay, control and simulation loop is a loop specifically used for modeling and simulation. Okay, it has certain, you know, parameter configuration. Okay, that is when you click on it. Okay, ideally used to perform simulation options and modeling options and solving the model. Okay, so like when we take any type of more mathematical modeling, okay, we tend to go for certain ordinary differential equations or something like that. We can create models out of ordinary differential equations. And now to solve that, okay, there is going to be some sort of algorithms which run. So in this case, this model control simulation loop is going to make use of ODE solver. Okay. So whatever transfer function or whatever you keep, okay, ordinary differential equation is going to solve them and give the response. So we can basically model or configure all these things, okay, with minimal programming. Okay, without minimal maths and minimal programming, we can solve the problems. Okay, like for instance, we have the simulation time. Okay, we can say how long the simulation is going to run and what type of model we are going to use. And more importantly, in simulation world, people may not consider the rate at which the simulation is running because the computer's processor is going to determine that. But in hardware, the resources is going to be very less because when we take an embedded system, it's going to have the IC and it's going to have a memory. I mean, clock pulse is going to be there, which is going to determine how fast the program is going to work. Okay, maybe you have an i7 processor, it has a 3 GHz or 4 GHz or 5 GHz. Okay, but a typical embedded system may have 667 megahertz or whatever. And even if we say okay, it's going to have RTOS, it's going to limit the execution rates. So how fast it's going to execute? Okay, that also will be simulatable. Okay, we have a discrete time option. So it's going to run at the rate of 500 hertz or 1000 kilohertz or 1 megahertz. Okay, we could specify them such that the simulation will run according to that. We can control all other type of parameters as well. We have timing parameters and whatnot. Okay, so it's a whole setup. We're considering all these things in mind. Okay, so let's say I'm going to run this at the rate of 1 megahertz. Okay, so I have to give it in terms of time, 1 e power minus 6. And here I want this to happen in my control. Okay, it should not be like 1 to 10 seconds only. I'll keep it as infinite such that the control in me in my hands. Let it run continuously. I should be able to control it. Now, how to create the model and how to create the PID and whatnot. So here PID, I mean, the only thing which can be reused is model, okay, not the transfer function. Again, transfer function can also be reused, but the way which you use the control simulation loop is going to be fairly bit easier, okay, because this control and simulation loop is optimized for control and simulation models. Like if you say in control system there's a gain, okay, we'll use this particular symbol. Summation means we'll use this one. Multiplication means we use this one. Okay, which makes it easy for us to convert something which we have done in paper to bring it into the program. Okay, that option is available here. And signal generation also it's available as a block. Okay, step signal you want to generate, you have it here. So something like that, it's available as a function. Now let's try to bring it here. Now to model the plant, I have something called linear systems. Okay, so there are other things. First, let's bring the model live. And here, if you see, there's a integrator, derivative, all these things are available. The one thing which is of interest for us is transfer function. The transfer function helps us model the transfer function on our own. Okay, the same thing, whatever we have done, the similar way we can do it. Okay, we have to give the input and output will be given get out here. So in order to make this modeling possible, I'll double click on this transfer function. And when I double click, this configuration window will open. Okay, the point of Labview is not a lot of programming entity should be approached. Okay, this configuration should be more focused upon. Okay, instead of typing everything as script, okay, here everything will be available as a block. And here, if you see here also, you can give the numerator value and denominator values. Okay, if you are interested in giving a such, you can do it. But as we already discussed, we don't want to reinvent the wheel again and again. Already this function is creating the model for us. So I don't want to again find the values and enter here. What I'll rather do is I'll click on this drop down box which says take from configuration box. All these values will be considered from here. Or there's also one more thing called as terminal. In this case, terminal means I can give the model output whatever you receive as output from here to input to this function so that it will automatically form the model. So I don't have to reinvent the wheel again and again. So here I get the input for a transfer function, which will connect from here to there. So we got the transfer function. Okay. Next is going to be PID. Okay, for PID, you can either use the already existing PID, or let's say if you want to create some PID on your own, perhaps you can do the same as well. Okay, first it will have having error signal. Okay, first you need to do the summation. Okay, so the set point versus the error signal here. So you can construct the whole control system block over here. And we want to implement parallel PID. Okay, in which case we'll be having a proportional gain, derivative gain, and integral gain. If you don't want integral, you can remove it. Or if you want to experiment it, try adding it. Okay, so all the inputs will go over here. Now, gain for the P, I, and D will be different. Again, to configure that, you will double click on this function of gain. And instead of getting it from the configuration box, I will give it as a terminal. Okay, in this case, I have to give one more input on top, which is going to be the PID gain, okay, KP, KI, KD. I have to do it for all. One second. Yeah, KP, KI, KD. So here we'll be having like this. Okay, so here you can right click and create a control and name this as KP. Name this as KI and name this as KD. Okay. So KP means proportional, means directly it will go. Okay, for integral, you can, if you want to consider integral, you can go for, integrator is available here. In continuous integral systems, will be an integral. You can either go for that, or basically you can create a transfer function model. Okay, you can double click on that and say it is 1 by S. Okay, 1 by S. And derivative is going to be S. Oh, sorry, this should be 1. Okay, let's try adding derivative. So now all these three should be added together and given as input to this transfer function. To add it, again we have a single arithmetic summation. Normally this will be, when I do summation, it's going to be like difference, it's going to do positive and negative. But again, you can always configure it. Okay, you can say we need 3 inputs. Okay, it's totally configurable. When you place the summation function, you can double click on it. You can say you need 3, and you can change them as well. What is the 3 also? Okay, when you click on them, it's going to say cycle. Okay, so 1, 2, When I click on it, it's going to change from positive, negative, nothing, positive, negative, nothing. So it's totally fully configurable. So all three I need positive. So I'll just give summation fully. And output of this is going to be here. And this is going to be given here. And the output of this is going to be here. This is going to be given as input to this particular function. So output of this is going to, you're going to get the angular velocity. Okay, but we're going to control the position. That's what we did before. So again, we need to do integration over here. So output of which will be connected over here. And there's going to be a slight addition at this point. Okay, that is, when integrating, sometimes the controls will go to unrealistically very large number of inputs. Okay, to avoid that, there are some non-linearity which we can introduce. Okay, like we can add certain saturation. So I'm going to control a motor, okay, with some sort of saturation. Okay, it should not go above or below plus or minus 5. Okay, so minimum value should be minus 5, positive value should be plus 5. So output of this is going to be feedback as the feedback over here. Now here we have to give the set point. Okay, for set point also, we have in control simulation, we have this signal generation option available. What type of signal you want to generate? Okay, that can be given over here. Okay, let's say I want to just try step value. Okay, you can try giving that. Okay, or you just want to keep changing the values. Okay, instead of giving now only one step, perhaps you want to keep on testing the steps. Okay, so you can try giving pulsing. Okay, so positive to negative, you can keep on going. Okay, that also you can give. So the DC motor is capable of rotating in both directions. So let me just try giving, use both positive and negative amplitude based. I'll use a signal generator, okay, where I can set a square wave. And here, if you see, it's going to be -1 +1 -1 +1. It's going to keep on going. So I'll be able to check, whether it is converging properly. Okay, this is going to be set point, and I want to look at the output, whether it's following the same or not. So let's see how everything plots together. I'm going to use a graph. Of course, I cannot use a direct graph. So in the same control simulation, there is a separate graph utilities for this kind of simulation environment. Here, if you see, there is a simulation time waveform available, which if you use, it will be better. Okay. So it will plot over here. So here we have Kp, Ki, and Kd. Okay, let's only start with Kp and check how it works really. Okay, it runs. Okay, maybe it's time to slow it down. Okay, try giving auto discrete time and let's check how fast it goes now. It still goes fast. Okay, here you can see it is, fine, but it's going too fast. Mhm. Okay, let's try varying the KD and see how it works. It seems like it's following. So when I increase the KD, right? But most of the time we need to, compare both of these values. Okay, we are only seeing the output. Okay, perhaps we need to check how the input occurs. Okay, so in that case, in order to look at both input and output, okay, what you can essentially do is use an array function and compare both input and output together. Or you can try um, restricting it to only 10 seconds. So you'll be able to see only for 10 seconds alone. So you could try increasing to 0.5 and see how it responds. So totally eliminating the Ki and increasing the Kd, you could see some sort of changes does happen. Yeah, this is fine. So This is input. I mean, this is the set point. And this is the feedback or the output. Which means that it's following properly. Okay, we are getting the closed loop system as such. So during the simulation, I believe so we set some certain values, okay, which I'm pretty sure that not all of them applied properly. Okay, it says 0.7. Here we use 0.2, and we did when we apply 0.7, you could see that it's grossly, it has a very large settling time. Let's try applying 0.2 here and check how it responds. It has a overshoot. Okay, so trial and error will be always there. And of course, this is running in a different sampling rate. Okay, so if you see, this does not include any sampling rate at all. It's a very simple system. But in this case, we are going to run this whole system, keeping in mind that this acquisition is happening at the rate of 0.00. This is the discrete time. If we consider this is how it works. Once this is done, this is going to be the algorithm which is going to be the PID control, which is going to control the actual system as well. Only thing we need to do is we have to replace this transfer function with, let's say, you can replace it with the DAC assistant. Okay, so DAC assistant is connected to a motor's driver. Okay, to get feedback again, you can use one more DAC assistant to acquire the data from an encoder. Okay, that could be fed as feedback over here. Okay, this could be the control signals. Okay, so let's say it's going to run at a particular speed. The speed data will be given over here. PID will process it. It will get the current speed. Okay, it will calculate the necessary steps required to achieve the speed, and PID will be in action. Okay, this will be continuous. So just with minor adjustments, okay, you could replace this simulated model with an actual hardware and control the real world data, real world hardware as well. Okay, so I hope this was understood. Okay, if you have any questions, please let me know. Let me check.
Any questions from the participant side?
Okay. So then next is going to be small discussion about how we can go about implementing and what are the embedded hardwares you can consider, okay, with minimal programming knowledge as well as graphical system implementation. So what next, right? So right now we have seen how we can model, how we can go about creating the controller, how we can evaluate the controller, then how we can run that in real time. Okay, when I say real time simulation can be done in the software itself. Then now we are going to discuss about how we can deploy the model. Okay, interact with the real world sensors and actuators and create the closed loop controls in real time. What are the things which we need to consider? Okay, so when we talk about implementing a deployment methodology, okay, we need to consider this. The control system, closed loop system, will happen in real time. Okay, when I say real time, it's not going to be quick. I mean, it's not going to be fast. Okay, it does not mean it's fast. It's going to be quick to respond. Okay, real time response is nothing but the ability of a hardware or software to respond, without any failure. Okay, and it happens within the guaranteed time period. Let's say if it's going to happen within 10 seconds, it should happen within 10 seconds. Okay, so most of the closed loop systems should respond immediately. Okay, so it should not have very large rise times. Okay, it should happen within the specifications of our requirements. Okay, so real-time applications, apart from closed-loop control, we have event response as well in safety-critical systems. Okay, in a oil rig, okay, if there are some faults, okay, it should immediately respond to that fault, maybe suppress that fault, or maybe report that fault immediately, such that lives could be saved immediately, right? So in order to perform such operations of closed loop system by software, okay, we should not prefer using a Windows operating system. Okay, perhaps we have to go for something which has high prioritizations, like real-time operating system. Okay, so hardwares with real-time operating system will be a proper fit. Okay, it will immediately respond, because softwares inherently could have delays, heavy delays due to operation. So when we are going to implement an embedded system with you know closed loop capabilities to interact with hardware, we have to choose a real-time operating system. That's why if you see Martian rovers, okay, so NASA or whoever operates such rovers, they will have systems with real-time operating system inside to monitor certain tasks. Okay, like VX works. NI itself has had a real-time operating system. And nowadays, Linux itself has a subcomponent of operating system called as real-time NX. Okay, we need to consider embedded system with such hardwares. So the reason why we go for real-time operating system is, apart from closed-loop control, to make decisions very quickly. After getting the control data, okay, how to immediately make decision, whether to turn right or left. Okay, whenever certain obstacle comes, we need to make decisions quickly, okay, in terms of microseconds. Okay, normal operating system, if you have used computers, if you want to open Word, okay, it may not open immediately. So that is not desirable in most of the cases. And your computer, we cannot run it continuously. Okay, 24/7 we can run to some extent, but some days we have to switch off, or we have to run updates. Okay, but that updates will not be planned updates. Most of the time Windows will really release that update on its own schedule, and we will get caught in it. Okay, most of the times we will get unplanned updates, and we may be in class, and that update will stall our class also. Okay, so that will happen. Headless operation. Okay, so most of the embedded system will happen, it will run its operation without user interface. It will operate continuously. It will have a remote user interface. Okay, the user interface will not be like laptop. If you see, it has a user interface built inside it. It is a display, right? So in order to program all these things, typically people will go for an embedded C based real-time operating system. Okay, where programming knowledge is highly required, and the skill which is required to develop such systems is going to be very high. Okay, but in order to make it simpler, Labview has a subcomponent called as Labview real-time system. Okay, where in order to program highly critical, highly modular, and highly reliable systems, instead of going for text-based programming tools, it's a LabVIEW itself. It is graphical program itself will be uh, make it possible to implement highly safety critical and closed loop systems in the graphical programming tool itself. Okay, where you can use host computer to control an RT target, a real-time target, which will act like a control system controller, right? So you can create the UI in your computer, okay, to control the level of tank or whatever, and interact with the hardware, which will have the IO sensors connected to it, get data, run the algorithm of PID or whatever, okay, and perform the plant operation. So in order to create closed loop system in LabVIEW based ecosystem, NI, that is LabVIEW's creator, NI offers certain hardwares. Okay, depending on your complexity, depending on the level of project requirements, different types of NI hardwares are available. Right. So yeah, if you have any questions, please feel free to ask. Okay, questions and answer session. If not, I will conclude this session. No questions. Okay, I will conclude the session. Thank you very much again, ma'am, for giving this opportunity.
Yes, sir. Thank you, Rajkumar sir, very much for the 2 sessions which you have handled on the hands-on Labview based on data acquisition and sensor integration, and also today's session. So it is based on control system design. So thank you very much for your wonderful sessions, hands-on experience sessions, sir.
Yes, ma'am. Thank you very much.
Thank you, sir. Dear participants, we'll close for the today's session. So I'll be sending the link for the attendance and the feedback. So kindly fill that. And tomorrow we are having the 5th day. So the first session will be the implementation of Industry 4.0 adoption in various sectors, and it's some case studies we will be taking up. And the last session will be on the stress management and emotional and physical health. So it is done by some doctor. So I'll request all the participants to kindly join the 2 sessions. So afternoon we'll be having a feedback and online test with the valedictory function. So thank you very much. So we'll close for the day.